So thank you for the introduction. I am indeed Lillian Childress, and I just recently started a new group at McGill University in January. So what I'll be talking about today are some experiments that I did while I was a postdoc collaborating with a group of Ronald Hansen in TU Delft. And I'm a physicist, and in fact, even worse, I'm an experimental physicist. So much of what this talk will be about are some of the engineering challenges around realizing more advanced quantum information applications. And in particular, I'll be talking about a particular physical platform, which is represented here by this red arrow. It's meant to represent a spin qubit in diamond that's associated with an optically active defect center. And the interactions between this system and photons allow you to prepare and detect the qubit states, and potentially also to engineer interactions between qubits located, well, macroscopic distances apart. Much of the motivation for working with this type of system, and in fact the reason why I got into this field myself about 10 years ago, comes from the hope of developing a physical platform for a quantum network. When I say a quantum network, I'm talking about a very vague and abstract idea wherein quantum information is stored in matter nodes, be they a harmonic oscillator or qubit type degrees of freedom, that are connected by some sort of quantum channel, which physically might be mediation via photons. And these types of quantum networks form the kind of basic structure for a variety of quantum information processing tasks. In the context of quantum cryptography, they may play a role in quantum repeater applications, where the matter nodes form a quantum memory that allows you to be robust to photon loss or perform entanglement distillation or error correction. And the quantum channels, of course, allow you to create entanglement over long distances. Or alternately, in the context of quantum computation, where these matter nodes might comprise several quantum bits over which you have complete single and 2-qubit quantum control. And the quantum channel provides a way to engineer entanglement between the registers so that you can engineer logical operations between quantum bits that are located in different nodes or in different registers. And what is physically required for these types of schemes ultimately boils down to having some physical system, some matter node, with ideally multiple controllable qubits or modes, and some mechanism to engineer entanglement between these nodes. Now, what would you actually want to build this out of? Well, there's many groups around the world who are using a variety of physical systems to explore these ideas, ranging from trapped ions or atoms, particularly in the context of cavity quantum electrodynamics, to ensemble-based atomic memories or ensembles in solid-state devices as well. And here I've stolen an image that you might recognize from one of the award-winning posters at this conference. This is even a possibility in the context of solid-state qubits. And I find the opportunity to work in the solid state very compelling from the perspective of being able to construct integrated optical and electronic devices. And the particular system that I study fits into this context, indeed under this category of solid-state qubits. And over the course of the next, 40 minutes or so, I hope I'll give you a picture of how the physical properties of this defect allow us to create a control over individual solid-state spins and also create an interface between the spins and photons. So with that, let me jump into some of the physics and give you a brief picture of this system that I study, which is the nitrogen vacancy center in diamond. Now, as its name might suggest, the nitrogen vacancy center in diamond is formed by a substitutional nitrogen atom next to a missing carbon atom or vacancy in the diamond lattice. And you can think about this very much like an atom, whatever your favorite atom is, or rubidium or sodium or hydrogen. And like an atom, there's electrons associated with this system, in particular electrons that occupy the dangling bonds of the defect. In the negatively charged state, which is the state that's typically studied, there's 6 electrons that congregate around this defect. And in their ground state, they have a net spin 1 degree of freedom. This is the spin that people talk about when they discuss the nitrogen vacancy center. And it forms a system into which by, for example, choosing two of the 3 spin projections, you could form a qubit. And for sake of argument, maybe you pick the ms equals 0 and ms equals plus or minus 1, one of the plus or minus 1 states. I should mention that please stop me as I go if I say something that doesn't make any sense or if you have a question. Okay, so, yeah.
Trying to understand this picture before you put the electrons on.
Yeah.
So I'm just trying to, being completely ignorant, understand this picture.
Indeed.
So normally diamond is only carbon.
Yes.
Pure carbon.
Yes.
Right. So one of the V is where there should be a carbon
Exactly.
atom, but it's not there.
Exactly.
Hence
yes.
a vacancy.
Yes.
And then there's this nitrogen, which is not in the vacancy. It's somewhere else.
It's replacing one of the other carbons. So it's like you took two carbons out of diamond.
So two carbons are missing.
Yeah, you take out two carbons and you put back one nitrogen, and then you have a nitrogen vacancy center.
Thank you.
Okay. And I should say, one of the nice things about, or one of the difficulties of working with diamond is when you have to transport your samples through security, you always have to be very careful to label them as carbon-based research samples. So we have a quantum bit associated with 2 of the 3 spin sublevels of the NV center. And in addition, we have an optically excited state, which you can actually drive transitions just by taking literally a green laser pointer will work and aiming it at this defect center in diamond. And when you do that, what's happening is that you're exciting both an electronic transition, really one of these electrons is changing its orbital state, and you're also exciting some vibrations of the crystal lattice. Those vibrations quickly decay, leaving the system just in its electronic excited state here. And so it fluoresces at longer wavelengths in the red. In fact, if you've ever seen a pink diamond, what makes that pink diamond pink are these types of defect centers. Now this, if we work with an ultra-high purity diamond, one that isn't pink, most definitely not, if you work with an ultra-high purity diamond, these types of optical transitions allow us to readily isolate individual defect centers. What you're looking at here is a scanning confocal microscope image of an electronic grade diamond, I think it was from Sumitomo, and it's taken by scanning a green laser over the surface of the diamond and counting the number of red photons that come out at each pixel. And the bright spots that you see here correspond to individual defects, as can be verified by looking at their photon statistics and emission. Now, these optical transitions are useful for looking at individual defects, but more importantly, they also give us access to the spin qubit. When you turn on the green laser here, in the instance right after you hit an NV center with a green laser, you're going to see slightly more fluorescence from the ms equals 0 spin state than from the ms equals plus or minus 1 states. And this gives us a mechanism to read out which spin state our qubit is in. And if you keep your green laser on that defect for a really long time, say maybe a microsecond or so, the spin polarizes into the ms equals 0 state, giving you an optical means to prepare a logical qubit. And if you combine this with the ability to engineer gates, single qubit gates, on this spin qubit using resonant microwaves, you can very easily observe rotations of our qubit as a function of the time of that microwave drive. And I should say this even works at room temperature, as we heard in a few talks earlier today and yesterday. Now, one of the interesting things about the NV center in diamond is that really it's not just this one qubit. In addition to the electron spin formed by the electrons that form the defect, there are also potential qubits formed by nearby nuclear spins. That is, there's a nuclear spin associated with the host nitrogen, and also diamond is mostly carbon, and carbon is mostly carbon-12, but on about 1% of lattice sites, you'll get an isotopic impurity, a carbon-13, and that has a nuclear spin. And so there's going to be some mesoscopic distribution of nearby carbon-13s. So for a given defect center, you can imagine having several quantum bits comprising the electron and a few nuclear spin degrees of freedom. And because you have spin transitions of the electron spin that you can control with microwaves, and those spin transitions depend on the configuration of nuclei in the surroundings. You can very easily engineer logical gates between the electronic and nuclear qubits and achieve the same level of control over nearby nuclear spins that you have over the electronic spin. Now this is pretty exciting, especially in combination with the coherence times that have been measured for these spins, which can reach, actually I think even exceed a second at room temperature for nuclear spins, and I think the current record is 580 milliseconds at cryogenic temperatures for the electron spins, which in comparison to the time scale in which you can manipulate them is really quite remarkable. So this has really excited quite a lot of experiments investigating quantum phenomena in various applications. Okay. But the experiments that I'd like to tell you about today fit within a particular vision for using the nitrogen vacancy center in diamond, in which you think about the electron spin and the few nuclear spins around it as a kind of matter node, a quantum register, where ideally we have complete control over these qubits. We're able to prepare them, manipulate them in single and 2 qubit logical gates, and measure them. But how do you scale up? Well, the hope is to be able to use the optical transitions of the NV center itself to engineer interactions over large distances. For example, if you could entangle the spin of an NV center with an outgoing photon, and do that for 2 different NV centers, and if you could get those 2 photons to interfere coherently on a beam splitter, then simultaneous detection of the photons can project the spins onto an entangled state and create the necessary channel between our 2 matter nodes. So the experiments that I'd like to tell you about today fit within this vision in 2 different ways. The first experiment is really an intra-node or intra-register experiment, where I'm going to show you how we're able to prepare with high fidelity and read out in a single shot the state of multiple spins associated with a single defect center. And the second experiment is aimed at the missing link in this long-distance entanglement scheme, which is to be able to generate or to observe 2 photon quantum interference between photons emitted by different NV centers. And so with that, my outline. It's been done in both now, but the first experiments were in the same diamond. So with that, optical spin readout, 2 photon quantum interference, and let's get started. So you might be wondering why I'm presenting optical spin readout if I just told you that it's really well known that you can use a green laser pointer to detect the state of an NV center. Well, it turns out that this conventional approach using green excitation doesn't give you a very high signal to noise for detecting the qubit. In particular, in a typical run, you might get a difference between the red curve and the black curve that's about, well, between 1/100th and 1/10th of your noise, depending on how good your setup is. So it's not a single shot detection of the quantum bit, although there's ways to repeat it that I'll talk about in a few slides that can work. Furthermore, the optical polarization is not 100%. Depending on the numbers you believe in the literature, it ranges from 70 to 90%. So when we began these experiments, it was an open challenge to figure out a way how to prepare with high fidelity and read out in a single shot the state of multiple qubits associated with an NV center. And to approach this challenge, we took a different tack. Rather than working at room temperature with a green laser pointer, we switched to cryogenic experiments that allowed us to probe the resonant optical transitions of the NV center. So let me say a few words about these resonant optical transitions. If you were to take an NV center and somehow magically put it in its excited state and let it fluoresce, the spectrum of light that it emits would look something like this. At cryogenic temperatures, you see a really sharp line at 637 nanometers that's associated with direct emission from that electronic excited state down into the ground state. And then there's a broad emission band that accounts for about 97% of the light coming out of the defect that's associated with both emission of a photon and a phonon. And this so-called zero phonon line at 637 nanometers, that's really the good stuff. That's the stuff where the light hasn't interacted with the crystal, or which path information hasn't been deposited in vibrations. That's the stuff that we want to probe. So one way to probe what's going on within that zero phonon line is to take a resonant laser and excite the NV center at various frequencies, basically scanning the laser in frequency across the zero phonon line while counting the number of photons in total that it emits. And when you do this kind of experiment, the data that you see looks something like this. There's a series of sharp resonances reminiscent of fine structure in atomic lines. And they have some very nice properties for accessing the electronic spin degree of freedom of the NV center. In particular, these transitions are spin selective. As an example, the two transitions that I've labeled here as frequency 0 and frequency 1, they can only be excited if the spin is in ms equals 0 for f0, or if the spin is in ms equals plus or minus 1 for f1. And actually, let's zoom in on those and forget about the rest, just to simplify things a bit. In addition, these optical transitions are also mostly spin conserving. That means that it's relatively unlikely for the spin to flip during optical excitation. And these two properties allow us to both prepare and detect the quantum state. To prepare the state, we take advantage of optical pumping, which is a well-known mechanism from atomic physics. Very briefly, what that means is that if we apply just one of these frequencies, for example, if we apply frequency f1, then if the spin started off in ms equals plus or minus 1, it would optically cycle for a while until the spin flipped, and then it would end up in ms equals 0, from which our light is no longer resonant and it can't be excited. And so this pumps all the spin population into ms equals 0, and we see a decay in fluorescence as a function of time. You can, of course, do the converse and excite on the other transition, and similarly see a decay in fluorescence. And by comparing the initial and final fluorescence levels, we can set a bound on our preparation fidelity as actually I think it was 99.7%, which is quite a big increase in fidelity over previous techniques. But there's something else that's interesting about this data, particularly for the bright red curve. If you look at the time scale, how long it takes for the fluorescence to decay, it's many dozens of microseconds. And the optical lifetime of the NV center is only 12 nanoseconds. So this defect center is undergoing many hundreds of optical cycles before the spin flip occurs. And this gives us a mechanism for reading out the spin. The idea is very simple, again, based on resonance fluorescence experiments in atomic physics. If you want to know the state of your quantum bit, then you send in light resonant with the F0 transition. If the spin happens to be in the state ms equals 0, you expect the defect center to emit many, many photons. Conversely, if the spin happens to be in ms equals plus or minus 1, you expect no photons to be emitted. And experimentally, the challenge is simply whether or not we can collect enough of those photons to distinguish the spin states before the spin flips. To do this, my colleague Hannes Bernien used a focused ion beam to mill solid immersion lenses into our diamond on top of pre-selected NV centers about 5 or 10 microns below the diamond surface. What you're looking at here is a scanning electron microscope image of such a solid immersion lens, and you can see from the confocal microscope inset that there's a single bright spot associated with our NV center in the middle of it. And using this integrated optics approach allows us to increase our collection efficiency by about a factor of 10, and indeed get into the regime where we can collect enough of the fluorescence to distinguish the photon state before the spin flips. Sorry, distinguish the spin state before it flips. So let me finally show you a little bit of data. If we begin by using optical pumping to prepare the spin into ms equals 0, and then send in our readout pulse, we see on average about 6 photons. Conversely, if we prepare the spin into ms equals plus or minus 1, we see less than 1/10 of a photon. This is a huge signal to noise, and it corresponds to about a 93% average fidelity for reading out the spin, which in recent years has been pushed up, I think, to 96% in the best case. Furthermore, we're confident that what we're measuring is actually the spin, because if we apply microwaves, expecting to see coherent rotations of our qubit, and then detect using this single-shot measurement at the end of the microwave pulse, well, of course, it's a single-shot measurement, so we get a bunch of ones and zeros. But if we average over many thousands of these experiments, we do indeed reconstruct the expected spin oscillations. Okay, so we can detect the electronic spin of the NV center. But can we detect nuclear spins around it? It turns out it's fairly straightforward to extend this type of readout to multiple spin qubits associated with a single defect. And to show you how this works, I'd like to walk you through how we do it for the simplest possible system, which is the electronic spin of the NV center and the host nitrogen nuclear spin, which is always there. Now, if I draw the level structure for this, don't get too scared. It's not that bad. I'm just going to draw the ms equals 0 electronic state and ms equals -1 electronic state with 3 possible nuclear spin configurations. And owing to the magnetic interaction between the electronic spin and nearby nuclear spin, the frequency for these 3 different transitions is different. And so if I send in microwaves that are resonant with, say, the transition that flips the electron spin only when the nuclear spin is down, I have a nuclear-controlled NOT gate on my electron spin. And so let's say that I start off with my system in one of these states, and I want to know what its nuclear spin state is. I want to read it out. Well, I can begin by optically pumping the electron spin, getting rid of that entropy, and then use my C0 gate to correlate the electron spin state with the nuclear spin state, so that when I send in my readout pulse, I'll expect to see fluorescence if the nuclear spin is in the state 0 or up, and not if the nuclear spin is down. Now, there's a subtlety here, which is kind of interesting. Certainly, the electron spin measurement that I've been discussing is not quantum non-demolition. It flips the spin in the process of measuring it. However, as I read out this nuclear spin state, I flip the electron spin, but not necessarily the nuclear spin. So I can repeat the measurement many, many times to get better signal to noise. This idea was first recognized by the Harvard and Stuttgart groups a few years ago in the context of conventional green excitation, and used to detect a nuclear spin at room temperature by repeating conventional measurements something like 2,000 times. Because the resonant excitation is so much more sensitive, we can attain the same fidelity using just 3 repetitions. But more importantly, we can do it in a manner that's compatible with sequential readout of multiple spin qubits. So to put this all together for you, I'd like to tell you about an experiment where we kind of, in my opinion, do it all in terms of preparation and detection of a 2-qubit register. We begin by using measurement of the nuclear spin to prepare the nuclear spin state and optical pumping to prepare the electron spin. And then we drive single qubit rotations independently for the electronic and nuclear spin degrees of freedom, before first reading out in a single shot the electron spin state, and then using that electron spin as an auxiliary qubit to read out the nuclear spin. And when we do this as a function of the rotation angle, let's see, I think the rotation angle for the electron spin is going to be on the y-axis, and the rotation angle for the nuclear spin will be on the x-axis. When we do this experiment, we see that the data for the electron spin indeed only depends on its supposed rotation axis, and likewise for the nuclear spin, indicating that we really do have single-shot detection of 2 nuclear spins in one experiment. It's a good time to ask questions now. No? Okay. Well, that's the last thing that I wanted to leave you with is that this isn't really the end of the story. This is really the beginning of the story for using NV centers for quantum information demonstrations. And very recently, the Delft group was able to use this type of single-shot readout to measure violations of Bell's inequalities using 2 nuclear spins associated with a single NV center in diamond, which really is kind of now it's become a benchmark measurement experimentally for demonstrating the level of control that you have over a quantum system. Okay, so that's about everything that I wanted to say regarding the first experiment, our ability to prepare and detect these quantum bits in a single node. But I think the challenge that faces this type of system, and indeed this is true across many quantum information processing platforms, is how to engineer some kind of scalable interactions between different matter nodes. And I walked you through the basic idea a few slides ago. But now that you have a bit of a better understanding of the nitrogen vacancy center, I'd like to give you a few more details behind the scenes of how you might go about it. In particular, if you wanted to entangle the state of 2 different electron spins associated with different NV centers, you might begin with the first spin-photon entanglement step. How might you achieve this? Well, in this particular case, I've written down a state where the spin of the electron is entangled with the presence or absence of a photon. This could be achieved by starting off with a superposition state of the electron spin quantum bit and sending in a pulse of light on just the ms equals 0 transition, so that you get a photon if the spin was in ms equals 0 and not if the spin was in ms equals 1. Okay, so if you can do that for one NV center, then you can do it for another NV center. And if you can get those photons to hit a 50-50 beam splitter, then something interesting can happen when you detect precisely one photon on one of the output ports. Now, I know the experimentalists are kind of groaning uncomfortably when I say this, but let's say that we can detect that there's precisely one photon in this system. Then that photon either had to come from the left NV center and not from the right NV center, in which case the spins would end up projected onto the state 0, 1, or the photon had to have come from the right-hand NV center and not the left-hand NV center, in which case the spins get projected onto 1, 0. And of course, here's where the magic happens. If we cannot distinguish the photons emitted by the different NV centers, then we have to allow for interference between these two paths. And rather than projecting onto a mixture of these two probabilities, we project onto an entangled state with a phase determined by the optical path length difference for the NV centers to the detector. Okay, so I hope this makes it clear to you why it's really important that the photons that come from the different NV centers be indistinguishable for these types of protocols. And the next experiment I'd like to tell you about really is aimed at this question of, can we get two different solid state defects to emit indistinguishable photons? Well, if we want to look at indistinguishability of photons, it means we want to do a Hongou-Mundell experiment. We heard very briefly about this, I think, in one line in the tutorial this morning, but let me go into it in a little bit more detail. If you want to measure whether two photons are indistinguishable, let's imagine the following thought experiment. Let's suppose we have two indistinguishable photons impinging upon the two input ports of a 50-50 beam splitter. I want you to think about the ways in which we could detect one photon in each of the output ports. Well, that could happen if both photons reflect or if both photons transmit. And again, this is where the magic happens. If we can't tell between these two possibilities because the photons are indistinguishable, then we have to account for interference. And it turns out that the laws of unitarity conspire such that any 50-50 beam splitter you can construct will always have a 180-degree relative phase shift between these two paths. And so they exactly destructively interfere, and it's simply forbidden for two identical photons encountering each other on a 50-50 beam splitter to emerge from opposite ports. And so experimentally, what we're going to be looking for is that our identical photons always come out together. It's kind of romantic. And the smoking gun that we'll be looking for is that these two detectors never fire at the same time. We're looking for missing coincidence counts. Okay. So if we want to see indistinguishable photons, it means that we want photons that have the same polarization, the same timing, the same spatial mode, and the same frequency. And it turns out the hard one is really this last one, getting two solid-state defects to emit photons with the same frequency. I already showed you the fluorescence spectrum of the NV center. And from this perspective, it's kind of a disaster because 97% of the light is emitted into this phonon sideband. So we're certainly going to have to filter out just that zero phonon line if we want to get two photons at the same frequency from different NV centers. But even within that zero phonon line, there's all these different transitions. Fortunately, we have a good enough understanding of the atomic-like structure of the NV center to be able to identify which of these transitions correspond to which spin states. And moreover, it turns out that these two transitions are orthogonally polarized. So we have a recipe now for getting our NV centers to emit identical photons. We'll excite them just with green light to make it easy, and then we'll spectrally filter the zero phonon line, optically pump the spin into ms equals 0, and this happens for free from the green light to a good approximation. And then we'll use polarization filtering to isolate just a single transition within the zero phonon line.
Sorry. We know the orthogonally polarized, but do we know how?
We have to calibrate that. So we can actually look at these types of spectra as a function of the position of our polarizers and see that one grows and the other diminishes.
But it would be stable.
Yeah. It's basically set by the crystal, the strain in the crystal at the location of the NV center. So in as much as that is stable, it's stable. Okay, so this sounds great, but there's a but. There's always a but, it seems. There's two things that we're going to have to deal with. And the first is that each NV center has a different type of fine structure. This happens because the frequency of these optical transitions is sensitive to the local strain in the diamond and to local electric fields. And any two NV centers are probably going to have different local environments. The second problem, which is even worse, is that if an NV center is sensitive to electric fields, then it'll be sensitive to fluctuations in electric fields as a function of time. And so if you look at just one of these transitions as a function of time, you can see it wandering around by far more than the natural line width. So we'll have to figure out how to cope with both of these in order to observe two-photon quantum interference. Well, to deal with the inhomogeneity between different NV centers, we again had two tools at our disposal. The first tool is to recognize that NV centers are sensitive to electric fields. So we can apply them and tune the NV centers into resonance. What you're looking at here is an optical microscope picture of our sample where we have two NV centers in different solid immersion lenses. And this yellow stuff here is gold, which are gates that we use to apply electric fields and tune the frequencies of the optical transitions. And by applying very moderate voltages, something like 10 volts, we can tune two of the transitions into resonance. So that's one tool. Another tool is to get lucky and happen to find two NV centers which have an optical transition that essentially overlaps. It's actually not entirely by luck. We spent a long time looking for these. And so when we apply our recipe, isolating that single transition within the zero phonon line, and then we take the photons that are these filtered photons that are coming from our NV centers and send them through a Fabry-Perot spectrum analyzer, we can see that indeed the two transitions are essentially on top of each other, but they're far too broad. They're about 500 megahertz wide rather than the 15 megahertz that we expect. And the reason for this is that at any given instant in time, the two NV centers are likely emitting fairly spectrally narrow photons. But as local electric fields fluctuate, they're moving around. And at any given instant in our experiment, then, it's quite likely that our two NV centers are emitting photons that actually have different frequencies. So how do we cope with that? Well, to cope with that, it's helpful to go back to this original picture of what we're looking for. We're looking for two-photon quantum interference, which is this funny, destructive interference between photons in this configuration. But it's actually not the fact that the photons are indistinguishable that makes this interference occur. It's the fact that the paths are indistinguishable. And what that means is that the photons don't have to be a priori indistinguishable. It means they have to be indistinguishable in principle to our detectors. And so we can exploit the intrinsic timing resolution of our detectors to erase the frequency which path information of the photons and recover two-photon interference. Don't worry, I will explain this.
In that case, wouldn't it be even easier to use two completely faulty detectors?
To what?
To use two completely faulty detectors.
They have to be in principle indistinguishable to the detectors. So the constraints that you're placing on it have to make it impossible for the best detector to distinguish. Yeah, that's a very good point. Yeah. Okay, but this was quite a mouthful, and so let me actually walk you through our experiment and tell you what I mean by time resolution in the context of a two-photon quantum interference experiment. So we have our two NV centers plus filters to extract that single transition within the zero phonon line. And we apply a picosecond pulse of green excitation to put them in the excited state. Now, most of the time, when we do this experiment, the NV centers emit photons that are in the phonon sideband or don't get collected by our collection optics, and nothing happens. OK, so we try again. About 1 out of every 10,000 tries, one of the NV centers emits a photon that gets through our filters into our collection optics, and one of the detectors goes click. But the two photons never got a chance to interfere, so we don't keep that data either. The only data that we keep are the 1 out of every 10 million events when both NV centers emit a photon that gets through our filters, gets collected by our collection optics, interfere on the beam splitter, and both detectors click. And what we do is we histogram the number of these events as a function of the time between them. That's what I mean by time resolution. And the idea is this. If the time between the clicks of the detectors is sufficiently short, then in principle, the photon detectors don't have enough time to distinguish the frequency of your photons. And so as a function of this time between clicks, we should see a suppression of coincidence counts right at tau equals 0. That's our signature of two-photon quantum interference. Okay, this is true, but actually I find this really unsatisfying. So I'd like to rewind to that moment when the two photons were about to encounter each other on a 50-50 beam splitter and think a little bit more quantitatively about what's going on. We know precisely what state the system is in. We have one photon on each of the two input ports of our beam splitter, so we can write down the quantum state. We're going to be detecting photons on the output ports of the beam splitter, which are related to the input ports by the beam splitter relations up to some factors of square root of 2. Let's say, for sake of argument, that the first photon is detected in output port 4. As we detect this photon, we're going to be annihilating a photon in mode 4 from our initial state. And that act of annihilation is going to project the remaining photon onto a superposition state of the two input ports. And in particular, it's precisely that superposition state which always interferes with itself classically to emerge on the same output port 4. So if experimentally what we're detecting is the probability to get a click in detector 3, well, immediately after that first click, it's just not possible. However, you'll notice I've drawn these arrows in different colors, and that's to remind you that these two photons might have different frequencies. And so, as a function of time, this superposition state could evolve. In particular, it will evolve as the difference in frequency of the two photons. So if we're monitoring the probability to detect photons at output port 3, well, as a function of time, that probability is going to oscillate with a frequency given by the difference frequency of the incoming photons. So this is what we would expect to see, and indeed this has been seen, for example, in experiments by Gerhard Rempe's group. This is what we would expect to see if we had NV centers emitting photons that had slightly different frequencies. That's not what we have. We have photons that are emitting NV centers that are emitting different fluctuating frequencies. And so when we take data, sometimes we're sampling from a distribution that looks like this, sometimes from a distribution that looks like that, and so on. And when you average over all the possibilities, the interference fringes wash out, and all that you're left with is a characteristic suppression of counts right around tau equals 0. That's our signature of two-photon quantum interference. Okay, hopefully that's a little more satisfying. And here's the data. It should look pretty familiar. What you're looking at in the top graph are a series of pulses associated with the repetition rate of our pulsed laser. And that's just because the coincidence counts will coincide with those. And if you zoom in right around tau equals 0 here, you do indeed see a suppression of coincidence counts with about 66% visibility, which is our qualitative indication of two-photon quantum interference. And I should mention that we understand pretty well what's going on. The red lines are a zero-free parameter simulation based on independently measured quantities. And we can do the usual control experiment by rotating a wave plate in front of one of the input ports of the beam splitter to verify that if we have different polarization photons, we don't see two-photon quantum interference. So we have a clear qualitative experimental signature. And there was a question about whether or not these NV centers were in the same diamond. Indeed, they were. But I should mention that a few months later, the Harvard group did a similar experiment with NV centers even in different cryostats. OK, so we're able to see indistinguishable photons. It seems like the stage is set, or more accurately, the stage was set for demonstrating entanglement between solid-state qubits at a distance. And while I was only distantly involved in this last experiment, I'd like to at least give you an idea of how you put together these tools in order to achieve this type of result. Now, if you remember back to my discussion of how you might generate entanglement at a distance using indistinguishable photons, there was this problem that I had to suppose that we were able to detect precisely one photon. And, well, that's simply impossible. Where there's no way that we can prevent the experiment from losing, in fact, a large proportion of the emitted photons. And so the actual experiment that the Delft group did followed this protocol up to this point, but they had to do something in order to compensate for photon loss. And the protocol that they followed is due to Sean Garrett. Where did it go? Oh, right. So I should say the effect of photon loss is that either the protocol worked and we got the entangled state we want, or both NV centers emitted a photon, we lost one and detected the other. And so we're in a mixed state that's a composition of the desired entangled state and the 0-0 state following this first round. And so to compensate for this issue, the experiments followed a protocol that was created by Sean Barrett and Peter Koch a few years ago, where they recognized that what we really need to do right now is eliminate this possibility. And in order to eliminate this possibility, we're going to need a second round of entanglement creation. In particular, if we flip the spins for both NV centers, this is a very simple single qubit gate for each NV center, then we end up in this situation where the state that we want looks roughly the same, but the state that we don't want is now in a state of the NV center that doesn't fluoresce. And so if we apply a second round of our protocol and we excite on the F0 transition, then in the state that we want, we expect there'll be one photon generated and we have a chance to get a click in one of our detectors. But in the state that we don't want, there's no photons generated. And so if we follow this protocol and condition on a second click in the detectors in this second round, then we eliminate the possibility that we're in the state that we don't want. And furthermore, in the process of getting that second click, we are again sensitive to the optical path length difference between the NV centers, but for the opposite states. And so we actually eliminate the interferometric sensitivity of the experiment and at the same time do a spin echo experiment on the spins. This is really a very, very nice protocol that Sean and Peter came up with. And this double detection was capable of generating heralded entanglement between NV centers that were located 3 meters apart on either side of an optical table with a fidelity of about 70%, well above the classical limit. But of course, like all p-squared protocols where you're conditioning on two unlikely events, it does suffer from efficiency issues. Yeah?
The fidelity of 70% is pretty good, but it's not good enough to do well in the quality test.
It's getting close. I mean, the classical, so the fidelity classical limit is 50%, just as a fidelity. But it's true we're not violating Bell's inequalities. So that's the next step to do a loophole-free Bell inequality test. So I should say, efficiency is certainly a challenge. And while this is a very nice story I'm telling you, does anyone want to guess the bit rate at which this entanglement was created? 1 for every minute? Yeah, 1 for every 10 minutes. I can't even do that calculation in hertz. So certainly going forward, it's going to be very important to figure out how to improve integrated optics to get these collection efficiencies up and make this a more practical system. So with that, let me just remind you of what I've been talking about, this vision for someday creating quantum networks out of NV centers in diamond mediated by optical interactions. And remind you that there's really a lot of things that need to be improved and that are kind of exciting to improve because they involve a lot of different physics and many different groups around the world working on these problems in different capacities. So with that, I think it's an exciting time for thinking about these types of problems, and I'd like to thank my collaborators at TU Delft, especially Lucio Robledo and Hannes Bernin, as well as my small group at McGill, and also you for your attention.
Thank you, Lillian. Do we have some questions?
What was the timing resolution of your detectors?
Yeah.
Lillian, can you repeat the question,
Okay.
please, for that?
So the question was, what was the timing resolution of the detectors, and what timing resolution did we need in order to erase switch path information? And actually, I can go back to that data, and then you can see for yourself what the timing resolution is. So the region in which you see 2-photon quantum interference in terms of time is set by 1 over the spectral diffusion line width. And so it's a couple of nanoseconds, about 500 megahertz for the spectral diffusion. And so that means that we would like to have detectors that are much, much faster than a couple nanoseconds. The detectors we were using, I think they were Perkin-Elmer SPCMs, and one of them had like a 400 picosecond timing resolution, and the other one was a little bit better. But it was just barely in the regime where actually we aren't so much limited by the timing resolution of our detectors as by background fluorescence from the other charge state of the NV center and residual imperfections in the spin polarization.
But if you had a much shorter timing resolution, you could hit back to time zero, which would be deeper.
It actually, in this case, it wouldn't help that much because the visibility is more limited by other factors, imperfect spin polarization and NV0 fluorescence. So in this case, we're right on the border where it doesn't make that much of a difference. But you're certainly right. If you wanted to look at things that had much wider bandwidth, then having faster detectors makes a big difference.
Wolfgang, give me a second.
You mentioned before that different NV centers emit at different frequencies. Is it obvious that the zero phonon line, the width of the zero phonon line between different NV centers is the same? And would that be is it obvious that the width of the zero phonon line, so the homogeneous line width of 2 different NV centers is the same? Would that be the same in the same crystal, or is it different if you go from one crystal to the other one? Can you comment on that?
Yeah, okay. So the question was about the width of the zero phonon line in different crystals depending on different local environments, if I understood correctly. And I think I should distinguish here between single center experiments and ensemble experiments. So when you're looking at single centers, it's hard to talk about the width of the zero phonon line because it's actually comprised of several distinct transitions. And so the line widths of the individual transitions themselves are much broader than the frequency over which the multiple transitions span. So typically the transitions will span over maybe 10 to 100 gigahertz, depending on the strain in the crystal. But the individual line widths can be as narrow as 100 megahertz or even less in good samples. In terms of ensembles, the line width of the zero phonon line depends greatly on the quality of the sample that you're working with. And if you were to take an ultra-high purity diamond, the electronic grade samples, and look at a bunch of different NV centers, it's hard to look at an ensemble because they're many microns apart. But the different NV centers would show slightly inhomogeneous lines that would shift by, I'd estimate, less than 100 gigahertz. For the ensemble homogeneity in ultra-high purity samples. In very dense samples that have many other types of defects in them, it can be a couple of nanometers. So it varies.
Okay, we have time for just one quick question.
How does the impact of spectral diffusion affect the ability to use these type of memories to build quantum networks? And what steps are you taking to mitigate some of the line width movements?
Yes, fantastic question. And I have the slide up to talk about it too. So the question was about what the effects of spectral diffusion, that is the limited time over which you see 2-photon quantum interference effects, what the effects are for quantum networks. And the simple answer is that it just decreases your efficiency because you have to gate your detectors so that you're only sensitive within that window where you can see 2-photon quantum interference and throw out the rest of your data set. So it just decreases your bit rate. Any imperfection in the visibility at tau equals 0 or within the window that you're looking at will decrease the fidelity. However, there are some tools at your disposal. One of the issues in this experiment, and I alluded to it with Michael's question, is that we were using green light here. And under green optical excitation, the spin polarization is imperfect. It's only about 90%. And we also have some possibility to be in a different charge state of the NV center that emits a different spectrum. And so if we excite resonantly rather than with green light, and in fact that's the approach that was taken in these entanglement experiments, then you can greatly reduce the spectral diffusion and actually increase both the depth of the two-photon quantum interference and the time scale over which it occurs. So
And the rates are what, approximately?
rates. The success rates here?
The spectral diffusion rates?
It's extremely fast under green excitation and very slow under red excitation. So the green excitation seems to lead to motion of charges in the vicinity of the defect.
Okay, I think we need to move on, but let's thank our speaker again.